All right, so in this video lesson right here, in this particular lecture, we are going to learn another technique for taking indefinite integral. It's just so we're gonna learn through this lecture as just learn another technique among so many techniques out there to handle an indefinite integral. Okay, and so specifically, the technique I would like to introduce in this video lesson here, in this video lecture here, is the technique that specifically apply to the family of trig integrals. Okay, so trigonometric integrals. All right, and so that's what it is. So you won't see the x squared or e to the x in here, but we're gonna be expecting a lot of these integrals are all having a lot of trig functions and heavily involving with trig functions. Okay, and so to get started now, let me brief through the idea, and I also have to mention ahead, trig integrals are challenging. It's just the way it is. Trig integrals are quite challenging, and so as we go along, right, and as in these modern day right here, many colleges and university math departments have already tried to cut down the amount of details we learn right here. And so what I deliver in this particular lesson here and the lecture here is some of the most common trig integrals being taught out there, being done out there, and then in some other video lessons as a continuation to this particular lecture, I will be able to deliver additional kinds of problem out there, okay, for trig integrals. Okay, so as far as what it is as a trig integral, now first of all, anyone at this point when you arrived at this the calculus lesson, this calculus video lecture right here, then you should be well familiar with these basic trig function. So sine of x or cosine of x, and from these two functions we build the other remaining four trig functions that made up the whole family of all six fundamental trig functions. So we have sine and cosine, and then we have tangent, and we have cotangent. And I don't think I need to remind anyone about what the meaning of these functions are and how we define them. And then there is cosecant, okay, and there is a secant function of x, okay. And so trig integrals is basically just we're looking at the integral on any function, and here I'm just giving some quick demonstration example over here. It could be a high power, like say fifth power of x. That is a trig integral. Or we are doing it could be among the trig integrals here. We could be working with tangent of x and secant of x. So we can have the kind of function we're working here could be a combination in the sense of a product where it came out as a combination of some two trig functions. And what's even worse, we even have to think about any of these can be raised to a power. So power 6 and power 7 on the secant. Those are the kind of functions. These are all quick examples of what trig integrals are all about. Okay, and so basically, throughout what I have learned from my starting days learning about calculus up until this point right here, and I have seen a lot, but just like alongside with what I have said earlier, so we are mostly going to learn to handle the kind of trig integrals where we have a high power or a power of a sine function. Okay, so sine to the n of x. That's one trig integral that we will specifically look at. We will also learn, so now a high power or a power of a cosine. of x. Okay, so we will be specifically looking at these. Okay, and then there are a mix between some power of sine and some power of cosine. Okay, and these powers don't necessarily have to be the equal power. Okay, so that's the kind of function that we're learning through. And then there are other trig integrals out there. Like say we're looking at a power of a tangent, or in product with a power of a secant, where these two powers don't necessarily have to equal. Okay, or we can have, so basically back at this quick list of the 6 basic trig functions, we can just quickly grab any function here, any one of these 6 trig functions, raise it to a power, and put it in a product with another with another trig function along this list here, in this list here, with a different power or equal power. Then we produce for ourselves a trig integral. So there are really a lot. And so back to what I was saying earlier, that there was a time that the students long ago had to learn through a lot of these, and any of these are not easy work at all anymore. But and some of these trig integrals have a definite method to follow, but some of the other ones have very unclear, specific, or definite methods to follow. And so at some point it's going to start becoming, the more creative you are, the better the chance you're going to get to that. And that's probably the reason why, that as time went on and up until this, in these nowadays, most of the time, these 3 classes, these 3 important classes, these 3 classes survived. And I mean survive means, these other trig integrals keep being ruled out from learning curriculum, and these 3 still remains and up until these days. And that's what I meant by survive. So these are still the one that being commonly taught at many colleges and universities, whereas these families outside of just the combination of sine and cosine, they keep being ruled out and ruled out. So in this video lesson, allow me to specifically focus on these the families of on these particular members of among the trig integrals, and then in a different video lecture as a continuation of this lecture right here, then I should be able to introduce a few more. And when it gets to this, I also have to admit I can never guarantee that I have learned enough in terms of experience to integrate all of these different situations right there of all of these different integral trig integrals. Okay, so here we go. Let's get started. All right, so now every example is a complete lesson. Every example being introduced here in this video lecture is a complete lesson, and it has its own methods in there. So how about, let me first particularly talk about the family that I wrote on the other board earlier. Let's look particularly at the family where it's one single trig function, sine, a power, some power, sine of x, some power of sine of x, or a single power of cosine of x. Okay, so this, of course, this family here also includes the simple one that we have learned, the integral of sine of x. That one here, we don't have to wait until this lecture to know. Quickly, this is negative cosine of x, and don't forget plus c. So that's just, a quick reminder right here. But this family is one among that. Okay, so that's at least it's some basic ground that we have to remind ourselves right there. And the same, that the cosine to the first power, which is simply cosine of x. This integral is also a family in this. It's cosine to the first power of x dx. And so this one here has a quick answer which everybody knows by heart up to this point, sine of x plus c. Okay, and so that's what it is for these 2 basic ones. And I don't need to call this as an example, as a formal example. It's just some quick reminder. Okay, so now at some point earlier prior to this video lecture, I also introduced, and I am quite sure that if this was an actual class of mine, then I also motivated my students to do a couple extra, it could be extra credits, opportunities that I asked my students to prove the following here, or I worked through some of these in my examples. But we have also seen a reduction formula. So either some of these was worked out throughout my example in earlier video lessons, or some of these are were asked by students to prove. I mean, some of these I asked the students to prove on their own because their experience at that point was enough. So I also need to remind a couple of things. Reduction formula, okay? So we had a reduction formula for sine to the n of x, okay? Sine to the power n of x dx. Okay, so as I said, this formula should have been seen in some of the earlier video lecture right there. And so the reduction formula says, and when it comes to formula, I tend to not memorizing it. So anytime it's about the formula, I always have to have the kind of reference page to remind for myself. So it's a minus 1 over n times sine of n minus 1 sine to the n minus 1 of x times cosine of x. Okay. And then I'm adding n minus 1 over n with the integral of sine to the n minus 1 of x dx. Okay, or let me rewrite it in a little bit of a cleaner version because I just realized I didn't use my board space very well over here. So sine to the power n of x, according to the reduction formula, it's a negative 1 over n times sine to the n minus 1 of x times cosine of x, okay, plus, and then sine n minus 1 over n to the sine to the n minus 1 of x. Okay, so that's the one reduction formula that I'm pretty sure that any of my students who follow along with my class have seen this, must have seen this. So I brought this up because I'm not saying that this is always the method, but it's a tool now. So at this point, and just along with my friendly warning that the trig integrals are not always easy. Okay, some trig integrals are, take some challenge. And so in that way, bring in as many tools that we already had as possible. So this is one of the tools right here. So when we need this formula, we use that formula. When we need some other formula, we use some other formula. And as a matter of fact, I can also mention, now this reduction formula is now in these nowadays, then they're all over the web with these integral tables and all that. The idea of integral tables is that they contain some integral formulas, making it easy for people to handle, because as I always tell my students, there are very challenging integrals out there that still remains completely a mystery for human mathematicians. And so we come up with so many different tools to handle integral problems. So using formula is just one technique right there. And so this formula does belong to the table of integrals, meaning there's always a sheet with and some sheets of integral formulas are more comprehensive than the other sheets right there. So just want to let you know that this can be found in any standard. This formula can be found in any standard integral table right there. Okay, and then alongside, so this formula is the reduction formula in a sense that when we're observing it, we can see that it starts out by finding the integral of some n power of the sine function, and then it has something fancy, and then it didn't really solve the problem right here with the formula, but at least it gets some part done, and then it produces another, this formula led us into another integral. But the good news about this integral is now it's in lower power. And actually I had a typo here, I just realized it needs to be -2 here. Okay, so it brings it, and that's why the formula here is called a reduction formula. So it doesn't solve the problem immediately, but it does bring the power down eventually, and then we can apply the formula again for this if we have to. Okay, if our integral is still, you know, have something else to waiting ahead. So in that way, this reduction formula is for sine, the power of sine. So we can also, we have another option right here. We have another tool as another reduction formula. Cosine, power n of cosine of x, okay, is 1 over n times cosine to the n minus 1 of x times sine of x. Okay, and that part here has no integral sign, and then plus, now we're going to go again, n minus 1 over n with the integral of cosine of n minus 2, cosine to the n minus 2 of x dx. And so this is, yes, ladies and gentlemen, it's another reduction formula, specifically good for a high power of cosine or a high power of sine right there. Okay, and so, but again, keep in mind, I only introduced these, and both of these are, you know, can be found on standard commonly throughout any standard integral tables out there. Okay, and so, and I'm mentioning that these are the tools, so it will, a lot of time it will work with these powers of sine and cosine, but I'm talking about just the individual powers of sine and cosine. Okay, and so now, in that way, allow me to start taking you into the first example. And as I said earlier, every example itself is a complete lesson on one technique on its own right here, because each problem has its own kind of problem that needs its own technique. Okay, so yes, I can now say that the two reduction formulas I showed worked on all of these powers of sine and cosine, but you know, we don't always have to use them, because sometimes if we have a better option, then we will use a better option. But yes, these reduction formula I just now erased will work, you know, at any time, because that's what they're for. So let me now bring in the first example to show you how effective they are. So let's now evaluate, okay, and this instruction of any example remains the same throughout the whole lecture here. So we're gonna evaluate this integral and that integral and this integral and that integral, so on and so on. So in example 1 here, let's look at how about cosine to the 4th power of x. Okay. All right, and that's the only one problem, like that, one single power, but power 4 of cosine of x. Okay, and so a couple things to notice. The power here is even. So now I have to admit, once you've learned through whatever methods I introduced here for this cosine to the 4th power, and it's an even power, that technique can also be applied for a sine function, because sine and cosine a lot of time work similarly. Okay, and so now as a general rule of thumb, anytime we have a high power of cosine, or sine of x, let's first try to use the reduction formula. So we already had that, I introduced that on the board here, that reduction formula, so that can be effectively used for this. So here what I see is n, the high power n here is 4. That's what this is. And the word even that I point to this power here is just something to trigger your observation. Okay, so with the power being 4x now, and I am going to use the reduction formula. So I am going to have the starts here. We are trying to find the integral of cosine to the 4th of x dx. Okay. So reduction formula says this is n, so we're going to need 1 over n. So now 1 over 4. And according to the reduction formula, it says we need to multiply with cosine, but no longer 4th power, now power 3, because cosine to the n minus 1, okay, of x. And then times sine of x. So that's just the formula. And I said prior to this lesson, I already had my students either proving it as an extra credit problem or formally as a problem like that. And then I had some other, and I might have had the reduction formula for sine, shown in some of my earlier video lecture right there. So you should have seen all of this before this particular lecture here. So 1/4, positive 1/4, and the 4 here comes out from that power, and then cosine of 3 to the 3rd power, 4 minus 1. That's why it's reduction. And then plus, and now n minus 1 over n. N minus 1 over n. So go ahead, you can feel free to pause the video and pull out that formula right there, write it down somewhere and follow along with me to see whether I have followed the formula correctly. But so now here it's n minus 1 over n. So n minus 1 is 3 over 4. Okay, n minus 1 over n. So that's 3/4. But we need to multiply with a different integral. So it's no longer cosine to the 4th, but now it's cosine to the, actually to the 3rd power. Actually square, okay, because it's n minus 2 here. So we applied the reduction formula once on this one, and we still ended up with a remaining integral here, which is unsolved by now. Okay, but look at ignoring all of these fancy things, and even also ignoring that 3/4 right there, then we can just simply see this as another integral of a high power of cosine. So now let's think about this as an n equals 2 right here. Okay, then we can apply the reduction formula again right here on this one. So here's how my integral currently looks like so far. So here I'm looking at the first term is a 1/4 cosine cube of x times sine of x. Okay, and then I'm going to add with 3/4, but the whole 3/4 here, the entire 3/4 stays in front of this integral as a coefficient. So I'm going to need to open parentheses, and then I'm going to specifically apply the reduction formula right here on this cosine squared of x. Okay. And so that gives me 3, and then in parentheses. Now I'm looking at, so now if n here is 2, right? N has been reduced. So n is 2, then now I'm looking at 1/2 times cosine, but 2 minus 1 is just cosine of x times sine of x. Okay, and now I'm going to need to add. So with my n, my updated n at this current step right here, it's n equals 2. So n minus 1 now is going to be 1 over 2, because n minus 1 over n, and with another integral here being cosine of to the 0 power of x, because it's n minus 2 for this extra integral here. But wait a minute, cosine to the 0, anything to the 0 is 1. So really all this here, I don't need to write it in that awkward way of writing it, but it's just cosine of 1 dx, and technically I don't even have to write that 1. Okay, and now I can move into the other board and to make some more space for myself. All right, so in the next step, the very first term remains the same. 1/4 cosine cube of x times sine of x plus, and that's 3/4. Now I'm going to multiply, allow me to swing back to the other board again. I am now going to multiply this 3/4 with these two terms right here. Okay, as distributive law, simply as distributive law. Okay, so now that means on the other board I should have written So 3/4 times a 1/2 is going to give me 3/8. Okay, and then that term there is cosine of x times sine of x plus, and now 3/4 times another 1/2 according to the other distribution of the term right there. Then it's going to be another 3/8 here multiplied with the integral for dx. Okay, so that's what it looks. So one more time let's have a look back at this one right here, and that's how I got 3/8 here, and I got so 3/4 times another 1/2, that's another 3/8. Okay. And now when it gets to this point, then we can no longer, then we no longer have to use the reduction formula, because this integral is simple. Okay, it's just the integral of 1 times dx, as we have seen earlier. And so that means first term here is 1/4 cosine cube of x times sine of x, okay, plus 3/8 times cosine of x sine of x, okay, and plus, and now all of this here just simply becomes, at this point in your experience in taking integral, it's a 3/8x, okay, no more sine or cosine at the end right here, and then that's the end of our antiderivative. Put a plus c in there. Okay, so that's the answer. So now what we've learned from this example right here, we've learned how to use the reduction formula, okay, and so just like I have what I have said earlier, then anytime we have an integral problem where we're integrating a power of either sine or cosine, then yes, right there you can always use the reduction formula. So if it's a cosine, a power of a cosine, you use the reduction formula for cosine, for power of cosine. If the problem here is a power of a sine function, then use the reduction formula for a power of sine function. Okay, so somebody says they like the reduction formula, somebody say they don't. Okay, so but at least it's worked. And of course, be ready that to accept the fact that the higher, sometime in the worst case where you have to do the similar problem but of a much higher power here, like say power 8 or power 10, do expect that you will have many steps to apply the reduction formula, and your final integral, your final answer will become a lot more lengthy than this. Okay, but now that's how we can effectively use the reduction formula on any power, either sine or cosine. Okay. And now let's look at example 2 here. We are going to evaluate, yes, it's another trig integral being given here for us. So how about sine to the 5th of x, okay, dx. So it's another function in that family, a power of either sine or cosine, and it's an integral problem right there. Okay, so just like what I have explained after example 1 right here, yes, definitely the reduction formula will work. So here's briefly how it works right here. Starting out with sine to the 5th, okay, we can use the reduction formula for sine to the nth of x, and turning this into a negative 1/5, okay, and we have sine to the power 4 of x, and then times cosine, and then plus, and now we're gonna, so that's power 5 right here, and then here we're gonna need 5 minus 1 is going to be 4 over n, which is 5, so 4/5 right here, and then we now producing an extra another integral here where the power is reduced down to the power of sine is reduced to 3, so sine cube dx. So that's one. So that means, as you can see ahead, that you need one more step right here. You need one more step of applying the reduction formula. So let's get it done. So now I can see that this, so at the start we had here n equals 5, okay, and then after using the reduction formula, the n power is reduced and updated to down to 3, and that's why it's called reduction formula. Okay, so again, I just want to enforce that reduction formula will always work on these single powers of a sine, either a sine or a cosine of x. Okay, and so here in my next step, so that term here is done. It's a negative 1/5, okay, times sine to the 4th of x times cosine of x plus, now 4/5 here is now a coefficient. So now I'm going to apply the reduction formula again here for this sine cube of x. And so that means I'm going to open a pair of parentheses. So the reduction formula says, with my current n right now being 3, then I need a negative 1/3. Okay, it's a negative 1/3 times sine squared of x. Okay, and times cosine of x. And then I'm going to need to produce, so everything here is inside a big pair of parentheses with the 4/5 in front. So this reduction formula that I'm applying is only for that integral of the sine cube of x. So in this way right here, we're going to reduce that power here. So this becomes, now as far, this is 2/3, okay, because n is 3, so n minus 1 over n, okay, times the integral, but now the power is reduced to just sine of x power 1. And that's what it means by reduction formula. So in every step, it's keep reducing the power of the remaining integral right here. Okay, and so now this one here, we don't need to apply the integral any longer. We can just go ahead and find the answer right out from this, because anyone know this one by heart. Okay, so and that's the point of the reduction formula. It's pretty effective. It's keep reducing your integral into the lower power, and lower power, so that at some point it's going to run into something that you're so familiar with. Okay, but now let's distribute out this 5/4 right here. Okay, and to create the another step. So now on my other board, right, the first term is still that negative 1/5 sine to the 4th of x cosine of x. Okay, plus, and now 4/5 is multiplied with the terms in there. It gives me, so now it actually becomes a minus 4/15. Okay, sine squared of x cosine of x, right, and then plus, and now I'm looking at 4/5 times 2/3 there. It's giving me 8/15 with the integral of sine of x. So I'm just rewriting the integral here after that distributive law right there. So now this integral is so ready for the final answer. So here I'm looking at, so first term is negative 1/5 sine to the 4th of x cosine of x minus 4/15 sine square of x times cosine squared of x plus, so now, and actually it's not a plus here, it's going ahead and become minus 8/5. Okay, and our answer here is a cosine of x. And then now when we're done with taking all antiderivatives, don't forget to add the final c right here. So that's our final answer. Okay, so this is how we got our final answer using the reduction formula. But now, just like what I said earlier at the end of example 1, some people like reduction formula, some people don't. I was one of them. I was among the people who didn't like to use reduction formula, and when it was my time started to learn, because I see it has to apply the same formula but step by step, and so it can get lengthy. Okay, it can get lengthy, and so in this particular problem, allow me to introduce an alternative. Okay, and I'm talking about another formal solution that's completely bypass the reduction formula. So we don't. So there's other methods I'm about to introduce, but only in this example. Okay, so only in this example that I can introduce another method that bypassed the reduction formula. Now, not in the first one. In the first one, we could not use any other, and there was no other technique more effective than the reduction formula. But this one here, we do have an alternative that's as effective, or somebody even like it better than using the reduction formula here. Okay, the reason that there are people who don't like formulas because integral tables are not always available with them. Okay, and plus some professors do not encourage using the tables as well. Okay, some professors would like their students to push their creativity beyond their beyond the expectation. So some professors don't approach too much with integral tables. Okay, and so now in case your formula is not there with you and the integral tables are not there as well, your formula is not memorized, okay, then you can also have an alternative. So I have to point out that in this particular in this particular problem, it could be a sign here. So in here it's a sign. It could the technique I'm about to show here, the alternative I'm about to show here, also works for a cosine. Okay, but what's important I see here is single power and it's odd. Okay, it's an odd power. So with this odd power here, here's what we can actually do. So taking advantage of the odd power here, then the first step I'm actually rewriting it. So actually, to maximize my board space, I'm gonna to use the most of my board space, I'm gonna write the next step here actually. So being the odd power, I'm always gonna save out. I'm gonna save out one power of the sign here, meaning, or I'm gonna separate out one power of the sign. So meaning now I'm looking at sine to the fourth of x times sine of x and the dx. That's what I meant by saved out, or leave out, separate out a one single power. So one power of x, leave out one sine of x here. So the remaining part here has to be, of course, sine to the fourth. Easy arithmetic. Okay, simple arithmetic here. So what's the next step? So here's the part. Now notice that sine to the fourth is the same as sine to the fourth is the same as sine square and squared again. So if it's to the sixth here, I'm gonna purposely write that as sine squared to the third power. If it's an 8 here, after separating out, so I'm talking about after separating out, and we will always end up with an even power here, an even power. And then I'm going to purposely see that even power here as a square, and then being raised to some other power here. So here, because it's power 4, I'm seeing that as a sine squared, but being raised to the power, another power 2. And then the other sign is out here. Okay, so now, at this point, I'm going to remind anyone about one thing that we have. Sine square of x, we have a famous trig identity that sine square of x will permanently equal to 1 minus cosine square of x. So in the next step, I'm rewriting that as 1 minus cosine squared of x. And all of that there being squared due to that power, and we're still having this separated sine of x being left out there. Okay. So it seems like we're making things growing more complicated, but here's how the next step coming in, and you will be surprised. Now, in order to use this method, I highly recommend you watch this after you viewed or have learned from my other video lessons about how we use the substitution method. Okay, so, or in case you haven't learned about the substitution method, then, or in case you already learned but forgot and arrived at this, I want you to pause the video and go back to my video lesson on the substitution method to understand some concept of that, and then go back to resume the video here so that you can see how I use the substitution here. So back in the days I was saying, there's no right or wrong substitution. Yes, it's still the same way. So here as a choice, and see, people in the past took a lot of time to work, and then they built their experience, and now they pass it down to us here, and so we use that. We think that as the way, but when people at the first generation doing this, they were doing that as exploring work right here. They try one substitution, it didn't work out, they try another one. So here, the best one to take here is I'm doing a u substitution for cosine of x. This cosine of x. And so according to the method of substitution, if we substitute cosine away, I mean once we assign cosine for another variable, for an external variable, then yes, we also need to find the derivative of u as a function of x in terms of x. And then so that gives me minus sine of x. Okay, but that also means further that du, I mean this equation can be rearranged as du over minus, and I'm running a little short at space here. Okay, so du dx. Okay, and then in the next line it can be du over sine of x. Okay, and indeed it's minus du over sine of x, and all of that there will equal dx, because at this point you are well aware that each one of the symbol here itself also means it's a fraction. So now the fraction of the two differentials du over dx, so now we can rearrange that and turn that into du multiplying up here and dividing both sides by negative sign right here. And so I consequently added up with dx is to equals with a negative du over sine of x. So by doing that, my integral becomes thus inside the square here is now 1 over u squared. Yes, it takes me some explanation, some explanation, because I have to also remind people about what do we do if we substitute it. Okay? And then all of that dx here, so we have sine of x times dx is substituted by minus du over sine of x. Okay, and so in that way, the sign cancels. And by the way, I had that sign remain, that sine of x remain because we didn't substitute that. But now after the substitution for dx away, that cancels nicely and the minus signs appears in front. Okay, so the problem turns out for us right here, it's a minus the integral of 1 minus u square du. And now it's going to be an integral that's a lot simpler. It's a lot simpler. So on my other board, picking up from where we had last step right there, then that integral 1 minus u square can be FOILed out. I mean this particular function 1 minus u squared can be FOILed out into a polynomial in terms of the u variable. And by the way, at this point we are completely at an integral in terms of a brand new variable. So here we're looking at minus, okay, 1 minus 2 u squared plus u to the fourth, okay, du. All right, and anyone can always pause the video to get yourself caught up with my algebra work right here, because allow me to assume that people at this video, arriving at this video lesson, should be fluent enough, fluent enough with the algebra, see how I FOIL this out. Okay, so feel free to pause the video and to find out how I got this. You can simply see that as a 1 minus u squared times another 1 minus u squared right there. That's what happened to the square right there, and then do your FOILing work to arrive there. Okay, and so now the integral is ready, and so it's going to be, I can also distribute the term in there, but it's not too important. So it's going to be minus 1/2. Actually, I'm lying. It's minus u for the first term because it's really after the integral. It's a u, but with the minus signs right here. And then now it's going to be plus. It's 2 u squared, but after taking the integral and the plus sign here because the minus with that minus. So now it becomes 2/3 u cubed. Okay, and then now it's going to be a subtraction because minus sign with that plus sign is a subtract. So now 1/5 u to the 5th power, and then plus c. Okay, but then it's not quite. We're not quite at the final answer yet, because what's wrong with this final answer? We are not with our original variable x. Here we're at some variable u. And so that means now I have to bring back the substitution expression, the substituted expression for u right here. So u was substituted as cosine of x. So in that way, now my expression, my final answer is as following. It's minus cosine of x plus 2/3 cosine cube of x, because that's what u cube is, plus, minus 1/5 cosine to the 5th of x plus c. Okay, and yes, ladies and gentlemen, this is another final answer for our beginning integral, and it's a solution that's completely in a completely different direction from using the reduction formula. Now, if anyone is worried about the fact that this final answer looks quite different with the final answer we've had in the same problem here, but when I was using the reduction formula, then feel free to pause the video and do some algebra on the trig function, and then you should be able to arrive at the same answer. But and any one of you, if you're learning directly with me, you can always get a hold of me to clarify. But you always have one famous technique. Doesn't matter how your final answer looks like. You always have one solid way to double check yourself. Take the derivative of this final antiderivative for here, of this final indefinite integral, term by term. And as long as we land, after taking the derivative, as long as we land into the beginning one being simply a sine to the 5th, then we knew that we found the correct answer. The same with any of the earlier examples that we have done. Okay, but so that's how we've done this with a completely different approach other than the reduction formula. So now the idea now is that I put the word odd here to specifically address that this method I just showed here only worked. The method that we saved out, that we separated out one sine, either sine or cosine, it's only worked when our function here was in odd power. So it could be sine here, it could be cosine here. So just like that, as a quick example, if you're looking at cosine to the 7th of power x, yes, the reduction formula will work just fine with this. But in case you don't like the reduction formula, then you can rewrite this as cosine to the 8th of x, and then separate out, to the 6th. Cosine to the 6th of x, and then separate out that extra cosine here. And so that this will become, so again, this is cosine, I'm purposely seeing that as cosine squared raised to the cube power. Cosine squared of x raised to the cube power. That's what this cosine to the 6th is. And then multiply with the cosine of x. And then in the next step was that we took here, cosine squared is the same as 1 minus sine squared. So these steps should be very similar to each other. And then here you are suggested to, here the intention here is to substitute sine. So I'm going to let u equal sine of x. See how fast it happens right there? Okay, and then we do all the substitution methods steps along with that. And so this problem will come out quite quickly right there as well. But again, sadly, this technique right here, aside from the reduction formula, this technique only works for odd power of either a sine or cosine. Okay, so that's how it is with this problem that I introduced here in example 2. And so now, after 2 examples, let's put up some generalization here regarding that general form here. So generally, when we are at the integral of a one single power on the sine, okay, power n of sine to the n of x, okay, or cosine to the n of x. Okay, this is a generalization that I would like to point out after working on 2 examples. And so yes, as a primary solution right here, use the reduction formula. How about let me state it. Let me state it as use the corresponding use the corresponding reduction formula. So if it's a sine to the n, use a formula, the reduction formula for sine to the n of x. If it's a cosine to the n, if your problem is a cosine to the n, you can use the corresponding reduction formula for cosine. And that's what I mean. And this, the reason I'm writing this in red here, because it will always work. This solution will always work. But now in case, so as the next bullet point right here, okay, in a special case, that's if n, the power here, okay, is an odd number, and in standard arithmetic, an odd number is expressed as some 2k plus 1, okay, because 2k means it's 2 multiplied with an integer, so that's even, okay, because an integer, an even number is a number that's always divisible by 2, and that's why mathematically speaking, or arithmetic as the arithmetic of that, it's 2 times an integer, that's even. But now being odd, it's just always 1 extra from the even, and that's why it's 2k plus 1. Okay, so if in case that your power here, in any one of these two problems is an odd right here, then you can do the following. You have an alternative method. So this is just an alternative on top of that method right here, or in addition to that method. Only happens when n equals 2k plus 1. Okay, so this is what you can do. Let me bring that to the other board right there. So now let me separate out into 2 columns. If it's we have seen that earlier, if it's a sine to the n and n is odd right here, then basically it's a sine of 2k plus 1 x dx. And so we purposely rewriting that as we separate out 1 sine of x. So that means we rewriting it as sine of 2k to the power 2k times 1 single sine. Because that's what we did in separating out 1 factor of the sine of x right here. And same way right here, if it was a cosine, then starting with cosine to the 2k plus 1 of x, we can rewrite that as the integral of cosine of 2 to the 2k of x times a separate 1 factor cosine of x. Okay, and then in the next step, you see that that's even power. I'm going to purposely rewrite it as a sine square of x raised to the k power. So if it's a 6 here, if 2k is a 6, and that means we write it as sine square to the 3rd power, okay, times the remaining sine of x dx. And then here, if it's a cosine for like a 10th power, for example, so if 2k is a 10th, then we're writing that as a cosine square of x, but raised to the 5th power, okay, and we're still going to multiply that with that lone factor cosine of x. And then the whole purpose of doing this, and I don't know why I wrote, maybe because I was thinking of 10 earlier, but k, okay, and then that means here when we express these as a square of sine or square of cosine, then we can re-express this as a 1 minus cosine square to the k power, okay, times sine of x dx, and then this inside the parentheses we can rewrite it as 1 minus sine square of x to the k power, okay, times the lone factor cosine of x. And so the advantage for doing this now is that we can, if we started out with a sine function, and when we ended up with something like this, then we can substitute u for cosine of x. That's the substitution. Okay, and here we can substitute u with sine of x, and then proceed on to follow the substitution method. So we can use the substitution method here. Okay, and so that's a generalization of how we work on these single power, okay, of either a sine or a cosine. All right.